All right, let's talk about finding zeros of a polynomial function. In previous videos, we've talked a little bit about complex zeros, so we're going to point out a couple of details about those first, and then we'll show you sort of some basic problems about finding zeros of a complex number or complex function. Polynomials, again, can be written as expanded form polynomials, or they can be written as sort of factored form. So one thing we want to do is be able to talk about complex zeros occurring, again, in conjugate pairs. We've got a good example up top here. We've got an x squared, we've got an x minus 3, and we have x squared plus 16. Well, again, the x squared is going to have two different zeros right at 0, right? So I can actually say 0 here. Right? And in our linear factorization, right, that's just going to stay, right, very simply, x squared, because technically it would be x times x. Now, if we want to get really fancy, I guess we could be very specific. We can make sure that we say x times x there. But again, most of the time, even at that rate, you're going to still see the book even say that that's x squared. X times x is easy enough to separate. We also have an x minus 3, right? That's a linear factor. But again, it's only a single zero this time, right? So again, a negative 3. So again, if we're listing off the zeros, I would say there's a couple of zeros, and then we're also a positive 3 there. Right? But then the x squared plus 16 is where it gets a little bit fancy. Again, our degree is saying, hey, there's two zeros here, there's 1 0 there. There should be two more zeros. We should be degree 5. There should be 5 total zeros going on. But again, x squared plus 16 equal to 0 means that x squared equals negative 16. And if we take the square root on both sides, x ends up equal to plus or minus 4i. So again, we're going to have plus or minus 4i as far as those zeros go. Zeros can be complex, remember. X-intercepts need to be real, but zeros of a function can be real or imaginary. Well, to write that as a linear factor then, we'd have to say x minus the positive 4i, as well as x minus the negative, or basically x plus 4i. And that would be our linear factorization there. Right? At the bottom, write a cubic function or cubic model, right? Cubic polynomial with zeros at 2 and 7i. Well, again, to be a cubic polynomial, right, there's got to be 3 zeros. And also we want to have real coefficients. So if we were thinking about, let's call it g of x, we were thinking about a function with these zeros, I can say x minus 2 because I need to have that 2 in there. I can say x minus 7i because if I plugged in 7i, that would make 0. But again, to have real coefficients, remember that I'm also going to have that 7i have a partner. It's going to have its conjugate pair. So always a good idea. Those imaginaries always come in pairs as far as that goes. Now, all of that explanation basically just helps us with a basic question like this. Find all the zeros of a given function, right? Then we want to write those as products of a linear factor. Once we can find the zeros, writing the factors is easy. But now the trick is to get started, the first thing we can do and the fastest way to start is go ahead and graph these functions. So I'm going to graph the function on the left, and you'll notice from our graph that it looks like we've got some zeros. Looks like over here, maybe at negative 2 is a good zero. Over here at positive 1, and then somewhere between 1 and 2, right? That one's going to be a little bit questionable. But that's where we can use our synthetic division to help ourselves out. So already, though, I'm going to kind of start my list. I think that negative 2 should be a good zero. So let's go ahead and synthetically divide out negative 2. We got to get our coefficients written down here. And we'll do some synthetic division. Drop the 2, multiplied by negative 2, and then add them up. Multiply and add, and we do get that nice zero of negative 2 verified. Then I'm thinking that 1 also looked like it worked pretty well, right? So I'm going to go ahead and drop down that 2 again. Multiplied by 1 is negative 3. Multiplied by 1 is 0, and it worked out just as well. So again, negative 2 and 1 are both definitely zeros of my function. Then finally, we went from third power, again, to second power. This is now first power, 2x minus 3. And if I want to find the zeros, let's just set that equal to 0. It means that 2x equals positive 3, and basically x equals, right, a positive 3 halves, right, is going to be one of my zeros there. So again, 1.5 or 3 halves should be my other 0. Now that's all really good work there. I'm going to go ahead and erase it though, because I'm going to need to write out the linear factorization, and I'm kind of running out of room here. So again, if you wanted to copy that down, feel free to rewind the video. You could always copy that down on paper. Pause the video as you go. But now to write the linear factorization, that means that f of x, right, it was f of x up top, it's still f of x, is equal to, well, I'm going to have an x plus 2, right, x minus the negative 2, x minus 1, and we could either say x minus 1.5, right, or we can think back to that factor beforehand. The trouble with what we have right now is we just lost our lead coefficient of that 2. Remember that previously our factor had been 2x minus 3. So the 2 was sort of multiplied in, right, to that factor, right? The 2 multiplied in here and times 2 multiplied in there, which is where this kind of came from. So if we're going to write f of x this way, we need to account for that 2. What I would do is throw it out in front here. If we don't do it that way, right, if that 2 is already multiplied into that factor, it's still linear. I would also take this as a way to write out f of x. And if you like that idea of not having that decimal in there, I would say that's a pretty good answer right there. Let's try the same idea with the equation we had at the right. Just another example here. I'm going to graph to start. You'll notice that -1 looks like a good answer. So I'm going to start my list. I'm going to risk it and call that -1. And then I'm going to go down here and I'm going to go ahead and start writing out -1 synthetically divided out of 1, 1, 9, 9. Let's see if it works. Right? We'll do the multiplying, and it turns out it works out very well. Right? Which leaves us with, again, x cubed becomes x squared. That's plus 9. Let's set it equal to 0. X squared equals -9, and x equals plus or minus 3i. So plus or minus 3i right there. So again, we've got our zeros, but again, to write our factors, or our linear factorization, f of x equals, we're going to say x plus 1, right? X minus the -1. X plus 3i, and x minus 3i right there. I hope that helps you dealing with finding zeros. Again, start by graphing. See what easy zeros you can get from the graph. You could also consider something like the rational zeros test. Feel free to look back at a different video for a description of that. But again, your calculator usually helps you fairly well with the easy to find zeros, the real zeros, right? Anything that's going to be a decent number there. Then synthetic division can help you either find those fractional zeros or possibly complex zeros. If you have any questions, talk to your teacher. Otherwise, good luck and have fun.